Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
Okay, so let's start with a box.
A box?
Yeah, the box. I know, you've heard this story 1,000 times. But we have to start here, right? Inside this box, there's a cat.
And a pretty grim little device.
Oh, it's diabolical. A single radioactive atom that might decay, a Geiger counter to detect it, and a hammer that, if triggered, smashes a vial of poison.
It is probably the most famous and definitely the most morbid thought experiment in all of science.
Exactly. And the punchline, the thing everyone kind of knows, is that until you open that box, the atom is in this weird state of both decayed and not decayed.
A superposition.
So the poison is both released and not released.
Yeah.
And the cat, well, the cat's somehow simultaneously alive and dead.
Schrodinger's cat. That's the poster child for quantum mechanics is weird.
It really is. And for decades, I mean, that's all it was, wasn't it? It was like a philosophical party trick, something to highlight the absurdity of it all.
It was. It was a paradox to show that the rules of the tiny quantum world made no sense when you scaled them up to our world, to cats and boxes.
It felt like an abstraction, something for physicists to argue about on a blackboard.
Right. Not for the real world.
But, and this is the whole point of our conversation today, on February 2nd, 2026, that's not the story anymore. That idea that it's just a weird puzzle, it's outdated.
It's completely changed. We've gone from the blackboard to, well, the motherboard.
Yeah. We're not talking about a hypothetical cat anymore. We are talking about the invisible engine powering, pretty much the entire modern world. The weirdness isn't a bug. It turns out it's the operating system.
That's a perfect way to put it.
And what's prompting this is a brand new piece that just came out in the journal Science. It's a perspective by Dr. Marlan Scully, and the title just says it all. It started with a cat, how 100 years of quantum weirdness powers today's tech.
And we should say, Dr. Scully is the perfect person to be writing this. He's not just a historian here. He's a major figure in the field.
Who is?
He's a distinguished professor at Texas A&M. He's got an affiliation with Princeton. I mean, if you've studied quantum optics, you've probably read his textbook. He's one of the people who helped build the bridge from the old strange theory to the new practical applications.
So he's seen the whole transition.
He's lived it. He's helped cause it.
Okay, so our mission today is to trace that journey. We're going to go back 100 years to when the smartest people on the planet were just baffled.
Completely baffled.
And bring it forward to today, where we use that bafflement to build things that honestly feel a lot like magic.
And we're going to break it down. We're not just going to list a bunch of gadgets. We want to get into the why. We'll talk about a concept called coherence, which is the secret behind every laser.
Okay.
We'll dive into entanglement, the spooky connection that Einstein hated, but that now protects your bank account.
And you mentioned it even gets into, breaking the rules of engines.
Breaking the classical rules, yeah. We'll look at how quantum mechanics is pushing the limits of energy efficiency. And then we'll get into some really unexpected places.
Like biology and weather forecasting.
Right.
I saw that in the outline, and it just seemed out of left field.
It is. But that's how deep this goes now. It's everywhere.
So if you want to understand the phone in your hand, the internet, even the future of medicine, you kind of have to understand the cat.
You have to start with the cat.
All right, let's do it. Rewind the clock for us. Take us back to the 1920s. What did the world of physics feel like then?
In a word, chaos. Complete intellectual crisis.
Really? I always pictured these confident guys in tweed jackets.
Well, maybe in 1900 they were confident. At the turn of the century, there was this feeling that physics was basically done.
The end of science idea.
Exactly. You had Newton's laws for gravity and motion. You had Maxwell's equations for light and electricity. You had thermodynamics. Lord Kelvin famously said there was nothing new left to discover, just more and more precise measurements.
Wow, was he wrong?
He was spectacularly wrong. Because as soon as they started probing the atom, the whole thing fell apart. All those beautiful classical rules just broke.
Give me an example. What's the first big crack that appears?
The electron. Okay, so we know an atom has a nucleus in the middle and electrons buzzing around it. The simple picture is a tiny solar system.
Right. Planets orbiting the sun.
But an electron is a charged particle. And classical physics Maxwell's equations are very clear about this. A charged particle moving in a circle has to radiate energy. It has to give off light.
Okay.
So if it's constantly losing energy, it should slow down, its orbit should decay. And in a fraction of a second, every electron should spiral into the nucleus.
Which would mean?
Every atom in the universe should instantly collapse. Matter shouldn't exist. You, me, this table, none of it.
Oh.
So clearly something was deeply wrong with the old rules.
The theory predicted we shouldn't be here to discuss the theory.
Pretty much. Bit of a problem.
So who rides to the rescue first? This is where Niels Bohr comes in, right?
Yeah. Yes. Niels Bohr from Denmark. He comes along and proposes this. Well, it was a radical idea. He basically just said the old rules don't apply.
He just declared it.
He did. He proposed his model, the one we all drew in high school chemistry. The little solar system with fixed rings.
Yeah, the nucleus and then shells for the electrons.
Right. And he said electrons can only exist in these specific shells, these allowed orbits. They can't be in between. They can jump from one shell to another, but they can't spiral in.
Why not?
He didn't really have a deep why. His answer was basically because if they did, atoms wouldn't exist, and they clearly do.
Yeah.
It was a brilliant patch. It was a Band-Aid that stopped the bleeding, and it worked remarkably well for explaining why atoms emit light in very specific colors.
So it was a good description, but not a fundamental explanation.
Exactly. It set the stage.
Yeah.
But the next step, the search for the real why, is where the drama really kicks in. This is the big clash of the 1920s.
This is Schrödinger versus Heisenberg.
The ultimate physics showdown. And they had completely different approaches to the problem. I mean, fundamentally different philosophies.
Okay, lay it out. Who's in the first corner?
In the first corner, you have the, let's say, the more traditional intuitive thinker, Erwin Schrödinger.
The cat guy himself.
The very same. He looked at the electron and said, look, maybe this whole tiny little ball idea is wrong. What if the electron isn't a particle at all? What if it's a wave?
A wave of
A wave of probability.
Yep.
A kind of smear of existence. He came up with the famous Schrödinger equation, which describes the electron perfectly as a wave function. And a lot of physicists love this.
Why?
Because we can picture waves. You can imagine a ripple on a pond. It felt comfortable. It felt like something you could visualize.
It's intuitive. Okay, it's not a hard little dot. It's a fuzzy cloud. I get that.
But in the other corner, you have the young, radical Werner Heisenberg.
The abstract guy.
The completely abstract guy. He looked at the data, which were these tables of numbers about how atoms absorbed and emitted light, and he basically said, I don't care about your pictures. I don't care about your intuitive waves. All that matters is the math that predicts the experimental results.
So you just focused on the numbers.
Only the numbers. He developed something called matrix mechanics, which was, I mean, it's just pure abstract linear algebra. Tables and numbers going in, tables and numbers coming out, no orbits, no waves, nothing to picture in your head.
And I'm guessing these two camps did not get along?
They hated each other's theories. I mean, truly. Schrödinger called Heisenberg's math repulsive and monstrous.
Wow.
And Heisenberg thought Schrödinger's wave idea was, I think the quote is, sentimental trash. He thought it was a cowardly attempt to stuff the weird new quantum reality back into an old classical box.
It sounds like an argument between an artist and an accountant over how to describe a painting.
That's a fantastic analogy. One is talking about the feeling and the form. The other is talking about the pigment codes and the canvas dimensions.
So who won?
That's the amazing part. They both did. It was eventually proven that there are two different mathematical formalisms were actually identical.
They were just two different languages describing the exact same thing.
Precisely. And the merger of those ideas, that's what gave us modern quantum field theory, the single most successful, most precisely tested theory in the entire history of science.
But, and this is the key point from Dr. Scully's article, for a long, long time, this was all just about describing things.
Right.
It was about explaining why the atom doesn't collapse.
Yes, it was passive. We were observers. We were looking at the quantum world and saying, wow, isn't that weird? Let's write down the math for the weirdness.
But the big shift, the centennial we're sort of celebrating here, is moving from observation to, what, application?
Utilization. We stopped just looking at the electron and we started putting it to work. As Scully says in his piece, it started as a way to explain tiny particles, but now it's driving innovations that were they were unimaginable a generation ago.
So we took the weirdness, the stuff that made them all argue, the paradoxes.
All of it. The uncertainty, the superposition, the spookiness.
And we realized they weren't problems, they were features.
They were tools. The best tools nature ever gave us.
Okay, so let's get into those tools. Dr. Scully breaks it down into three big concepts. Let's start with the first one. Coherence. I have to admit, when I hear that word, I just think of an argument that makes sense. I don't think physics.
It's a fair point.
Yeah.
But in physics, coherence is really about synchronization, harmony.
Okay.
To get it, you have to first picture what normal, everyday light is like. Think about a regular old incandescent light bulb.
Okay, got it. It's on. It's giving off light.
But at the atomic level, inside that filament, it's absolute chaos. The atoms are hot. They're jiggling around randomly. One atom spits out a photon, a particle of light going left. A nanosecond later, another one spits one out going right.
And they're all different colors, lightly.
Exactly. Different phases, different directions, different frequencies. The light waves are all jumbled up and out of sync. It's noise.
It's like a huge crowd of people all talking at once.
That's the perfect analogy. It's a noisy, disorganized crowd. That is incoherent light.
So what's coherent light?
Coherent light is when you somehow manage to grab every single one of those atoms and force them to do the exact same thing at the exact same time.
You turn the crowd into a choir.
A perfectly disciplined, perfectly synchronized choir. Every single light wave is marching in lockstep. Same frequency, same phase, same direction. The peaks of the waves line up. The troughs of the waves line up.
And when you do that, what do you get?
You don't get a light bulb, you get a laser.
The laser. It's funny, lasers feel so normal now. They're in barcode scanners. My cat chases a laser pointer. It feels like old tech.
It's totally ubiquitous.
Yeah.
But we can't lose sight of how completely impossible it seemed. I mean, when the idea was first proposed, based on an insight from Einstein, a lot of top physicists said it was practically impossible.
Why? What was the barrier?
They just thought that nature's tendency towards disorder, towards chaos, towards that noisy crowd would always win. They didn't think you could ever impose that much quantum order on a real-world system.
But we did.
We did in 1960, and that coherence, that order, is what gives a laser its almost magical properties. Because all the waves are working together, the beam is incredibly intense, and it doesn't spread out like light from a flashlight.
It stays in a tight, straight line.
A phenomenally tight line. I mean, we literally bounce lasers off of reflectors that the Apollo astronauts left on the moon to measure the Earth-Moon distance down to the millimeter. You can't do that with a flashlight.
Okay, that's impressive. But what about the everyday stuff Scully mentions?
Well, the barcode scanner is the most famous simple one. But think bigger. Think about medicine.
ELIS. Eye surgery.
Exactly. We are using a blade made of pure, coherent light to reshape the human cornea, to vaporize tissue with microscopic precision. That is only possible because of quantum coherence.
Or what about the internet itself? The whole thing runs on fiber optic.
Billions of miles of glass fiber with pulses of coherent laser light flashing through them, carrying this conversation right now. All of human knowledge flying around the globe as ordered photons.
It's mind-boggling that the solution to that 1920s argument about waves and particles is the reason I can stream a movie.
That's pillar number one. We learned how to tame the quantum wave.
Okay, pillar one, coherence, gives us the laser. Let's move to pillar two, and this is the one that, it's weird, entanglement.
Spooky action at a distance.
I love that Einstein said that. It sounds so unscientific. He just called it spooky.
It shows you how much it bothered him. I mean, Einstein was a firm believer in what's called locality. Meaning that if you want to affect something over there, you have to go over there and touch it, or you have to send something, a baseball, a sound wave, a beam of light to interact with it, and nothing can travel faster than light.
The cosmic speed limit.
The absolute speed limit. But quantum mechanics predicted something that seemed to violate this. It predicted that you could create two particles, say two photons, in a special linked state, an entangled state.
What does that mean, linked?
It means they no longer have separate identities. They are described by a single shared wave function, a single mathematical reality, even if they're physically separated.
So they're like one object in two different places.
That's a good way to think about it. Their properties are correlated in a way that classical physics just forbids. So let's do the classic example. You create a pair of entangled photons. You send one to Alice in New York.
And the other to Bob on Mars.
Let's go with Mars, sure. Alice and Bob. So while these photons are in flight, their properties are undefined. Let's talk about their polarization, like the orientation of the light wave. It's not horizontal or vertical. It's in a superposition of both, a cloud of possibility.
Okay, so it's undecided.
Right. But the instant, and I mean the absolute instant, that Alice in New York measures her photon and her detector says vertical, she knows with 100% certainty that Bob's photon on Mars, millions of miles away, has instantly resolved itself into the horizontal state.
Instantly, not in the time it would take for a light signal to travel from here to Mars.
Faster than that. Infinitely faster, it seems. The information, the collapse of the wave function, appears to be instantaneous across any distance.
I can see why Einstein called that spooky.
He hated it. He thought it meant the theory had to be incomplete. He argued there must be some hidden variables, like secret instructions the particles were carrying with them from the start.
Like they flipped a coin before they left and agreed, okay, if she asks, you're vertical and I'm horizontal.
Exactly. He thought it was a conspiracy, not a real connection. But here's the amazing thing. We've done the experiments over and over, and Einstein was wrong.
There are no secret instructions.
Nope. The spooky connection is real. The universe is non-local. It's just a fact.
Okay, so the universe is weirder than Einstein was comfortable with. We've established that. But how do we use this? What's the application?
The number one application right now is cryptography, keeping secrets safe.
Okay, so digital security.
Think about it. Our entire global economy, our military secrets, our personal data, it's all protected by encryption. And that encryption is based on math problems that are really, really hard to solve.
Like factoring huge numbers.
Right. But really hard isn't the same as impossible. A powerful enough computer, say a future quantum computer, could potentially crack our current encryption methods.
So all our secrets would be out in the open.
Potentially, yes.
Yeah.
It's a huge concern. But entanglement offers a way out. It allows you to create an encryption key that isn't just mathematically hard to break. It's physically impossible to copy or even listen to without being detected.
How does that work?
Okay, so imagine Alice wants to send a secret key to Bob. Instead of sending a string of ones and zeros, she sends a stream of entangled photons. Now, an eavesdropper, we'll call her Eve, tries to intercept the message.
She taps the fiber optic cable.
Right. But to find out the state of the photon, what does Eve have to do?
She has to measure it.
She has to measure it. And in quantum mechanics, the act of measurement isn't passive. It changes the system. The moment Eve's detector interacts with that photon, it collapses the wave function. It breaks the entanglement.
She leaves the fingerprint?
A giant, unmissable fingerprint. Alice and Bob can then sacrifice a small part of their key, compare notes over a public channel, and if they see a bunch of errors that shouldn't be there,
You know Eve was listening.
they know instantly. They throw away the compromised key and start over. It's like a security system that's guaranteed by the fundamental laws of physics.
It's like a message written in invisible ink that bursts into flame if anyone but the intended reader tries to look at it.
That's a perfect way to put it. And this isn't science fiction. Governments are building quantum communication networks. There's a Chinese satellite called Mischius that does this from space. We are building the foundations of a quantum internet.
That's wild. But the source mentions another use for entanglement that's bigger. LIGO.
Yes, the Laser Interferometer Gravitational Wave Observatory.
These are the giant detectors that discovered gravitational waves, the ripples in space-time from colliding black holes.
That's the one. And what they're trying to measure is almost impossibly small. A gravitational wave passing through Earth stretches and squeezes everything by a distance smaller than the width of a proton.
How can you possibly measure that? A truck driving by a mile away must shake the ground more than that.
It does, which is why the detectors are so isolated. But even with perfect isolation, there's a fundamental limit. It's called quantum noise, or shot noise.
What's that?
It's the fact that a laser beam, even a perfect one, isn't a smooth, continuous river of light. It's made of individual photons. It's like rain on a roof. There's a natural randomness, a statistical jitter to when the photons arrive at the detector.
So the laser beam itself is noisy at the quantum level.
Exactly. And that noise can be bigger than the tiny signal from the gravitational wave you're trying to hear. It's like trying to hear a pin drop during a hailstorm.
So how does entanglement help?
They use a very clever trick called squeezed light. It's a way of manipulating the Heisenberg uncertainty principle.
Oh boy. Okay, unpack that for me. Heisenberg says you can't know certain pairs of things perfectly at the same time, right? Like a particle's position and its momentum.
Exactly. There's a trade-off. The more precisely you know its position, the fuzzier its momentum becomes, and vice versa. Well, a light wave also has pairs like that. It has an amplitude, its brightness, and a phase where it is in its wave cycle.
Okay.
Using entangled photons, scientists can squeeze the uncertainty. They essentially say, we don't really care about the phase for this measurement, but we need to know the amplitude with insane precision. So they manipulate the quantum state to dump all the uncertainty into the phase.
You're hiding the noise in a part of the light you're not looking at.
You're sweeping the quantum dust under a rug you don't care about. And the result is you get a laser beam whose brightness is quieter, more stable than quantum mechanics would normally allow.
And that lets them hear the black holes.
It boosts LIGO sensitivity significantly. We are listening to the echoes of cosmic collisions from billions of years ago by using a quantum trick that Einstein thought was just stooky nonsense.
Okay, this is amazing. So, coherence gives us the laser. Entanglement gives us secure codes and a way to listen to the cosmos. This brings us to the third big concept from Scully's paper, and this one. This one feels like it's breaking a really fundamental rule.
There are dynamics, the quantum heat engine.
Right. Now, what I remember from physics class is that there's a hard limit, the Carnot limit, named after some 19th century French engineer.
Seti Carnot, yes.
And he basically said you can't build a perfect engine, you put heat in, you get work out, but you always have waste heat left over. There's a maximum possible efficiency, and you can't beat it.
It's one of the most fundamental laws. You can't get something for nothing, and you can't even break even. There is no free lunch.
But Dr. Scully's work seems to suggest there's a loophole.
A quantum loophole, let's be very clear. We are not breaking the law of conservation of energy. We are not creating energy out of thin air.
Okay, good. I was worried for a second.
But what Scully and others have shown is that you can design an engine that operates with an efficiency greater than the classical Carnot limit.
How is that possible?
It all comes back to coherence. Think about a regular engine, like a steam engine. The working fluid is hot gas, and those gas molecules are like trillions of tiny billiard balls, all bouncing around randomly and chaotically. That chaos is a source of inefficiency.
Disorganized energy.
Exactly. You lose a lot just to that randomness. But what if your working fluid wasn't a bunch of random billiard balls? Yeah. What if it was a collection of atoms prepared in a special quantum coherent state?
You're using the choir again instead of the crowd.
The choir's back. By using coherence, you can create correlations between the atoms that suppress some of that randomness. You could essentially channel the heat energy into useful work in a way that avoids the pathways that would normally lead to waste.
So the Carnot limit wasn't a fundamental law of the universe. It was just a limit based on using dumb classical particles.
It was a limit based on the assumptions of classical thermodynamics. When you introduce quantum information and quantum coherence into the system, you change the rules of the game. You're extracting useful work from a place that classical physics had written off as unavoidable waste.
That feels like a massive deal for energy production down the line.
It's a whole new frontier. We're not going to see quantum engines in our cars tomorrow, but it fundamentally changes our understanding of the relationship between information, energy, and work. As Scully says, it's a striking example of how quantum principles can rewrite the rules of classical physics.
It really is. Okay, I want to shift gears now. We've talked lasers, computing, energy. This all feels like the traditional domain of physics, hard tech. But the source material then goes somewhere I did not see coming.
Biology.
Yeah, it's so strange. I mean, my mental image of a quantum experiment is, a lab cooled to 1,000th of a degree above absolute zero, a perfect vacuum, everything shielded. It feels incredibly fragile.
That's generally true. The biggest enemy of quantum weirdness is the environment. It's a phenomenon called decoherence. The moment the outside world interacts with your delicate quantum state, it collapses. The magic vanishes.
And a living thing, a cell, is the exact opposite of that. It's warm, it's wet, it's messy, it's the noisiest environment imaginable.
And that's why for a long time the dogma among physicists was that quantum mechanics could play no meaningful role in biology. It's just too hot and wet for any of this delicate stuff to survive.
But it seems that's wrong.
It seems nature is a much better quantum engineer than we are.
The article mentions a specific technology here first. It's a mouthful. Coherent Raman spectroscopy.
It is. Okay, let's just break it down. Raman spectroscopy on its own is a technique scientists use to identify molecules. You shine light on a sample.
Okay.
When a photon of light hits a molecule, it makes the molecule vibrate. The chemical bonds stretch and wiggle. And that vibration steals a tiny bit of energy from the photon, which changes its color very slightly.
And different molecules wiggle in different ways.
Exactly. A sugar molecule has a different vibrational fingerprint than a protein or a lipid. So by looking at how the color of the light changes, you can figure out what chemicals are in your sample.
Sounds useful. What's the problem?
The signal is pathetically weak. Only about 1 in a million photons that you shine on the sample actually gets changed in this way. It's like trying to find one specific grain of sand on a beach.
So how does adding coherent to the name help?
You guessed it. It's the choir again. Instead of just shining a steady light, you use very fast, powerful laser pulses to force all the molecules of a specific type, say all the glucose molecules, to start vibrating in perfect unison.
You make the molecules sing together.
And when they sing together, the signal they produce is amplified by orders of magnitude. It goes from being a nearly invisible whisper to a shout.
And what does that let you do?
It lets you see biology happen in real time. The source mentions using it to map the chemical composition of a virus at the nanoscale. You can watch a drug molecule binding to a receptor on a living cell. It gives us a window into the molecular machinery of life that is just unprecedented.
We're upgrading from a blurry photograph to a live 4K video.
That's a great way to put it. And it's not just a tool we're using. There's more and more evidence that life itself uses these tricks.
Like in photosynthesis.
That's the prime suspect. For a plant to turn sunlight into chemical energy, that energy has to travel through a dense, messy forest of proteins inside the leaf. Classically, it should bounce around randomly and lose most of its power as waste heat. But it doesn't.
It's super efficient.
It's nearly 100% efficient.
Yeah.
And the thinking is that it uses quantum coherence. The energy travels as a wave, exploring all possible paths simultaneously, and instantly finds the most efficient route. It's performing a quantum search.
So my houseplant is running a quantum algorithm.
In a very real sense, yes. It's humbling. We spend billions on building these sterile labs to do what a simple leaf does in the sunshine.
That is incredible. Okay, so from the tiniest virus to a hurricane, the last application in the source is weather and turbulence.
The oldest unsolved problem in classical physics.
I just think of it as something that makes my flight bumpy. I didn't realize it was a deep mystery.
Oh, it's a monster.
Yeah.
Heisenberg is supposed to have said that when he died and met God, he was going to ask two questions. Why relativity and why turbulence? And he said, I really believe he will have an answer for the first.
So even Heisenberg thought turbulence was basically unsolvable.
It's just too complex. The chaotic, swirling motion of air or water, the equations that describe it are nightmarishly difficult. That's why even with supercomputers, our weather forecasts fall apart after a week or so.
So where does quantum mechanics come in?
It comes in by providing a simplified model system, a playground, to study turbulence in a cleaner way. Scientists are looking at something called superfluid helium. Yeah, it's a bizarre state of matter. If you cool helium down to just a couple of degrees above absolute zero, it transforms. It loses all viscosity. It has zero friction.
What does that mean?
It means if you swirl it in a cup, it will literally never stop swirling. It can flow up the walls of a container. It's a quantum fluid, where all the atoms are acting as one single coherent entity.
That's strange, but how does that help with turbulence?
In a normal fluid like air, turbulence is a chaotic mess of eddies and vortices of all different sizes. But in this quantum fluid, the rotation is quantized. It can only spin in discrete, identical units. These tiny, perfect tornadoes called quantum vortices.
So it's organized chaos.
It's countable chaos. You can study how these identical little vortices interact and tangle up to create turbulence on a larger scale. It's a much simpler, cleaner problem than trying to model the entire atmosphere.
And what you learned from the helium.
You find mathematical patterns and scaling laws that, it turns out, also apply to the big, messy, classical turbulence of our weather systems and the air flowing over an airplane wing.
So we're making flights safer and improving storm forecasts by studying the weird behavior of super cold liquid helium.
We are. It's this incredible through line. The same fundamental rules of quantum mechanics that describe that helium also describe photosynthesis and also describe the laser in your phone.
It's all connected.
It's all the same physics.
Okay, so we've covered 100 years. We started with the confusion, the fights. We've seen coherence give us lasers, entanglement give us security and black hole detectors, and thermodynamics give us a new class of engines. We've even dipped into biology and the weather.
It's been a busy century.
But Dr. Scully's paper, it doesn't end there. It's not just a look back. He ends on a forward-looking note. He says the adventure is just beginning.
Which is absolutely true. For all we figured out, the list of what we don't know is still huge.
What's at the top of that list? What's the biggest unsolved mystery?
Gravity, without a doubt.
Still. After all this time.
Still. We have these two perfect theories. We have quantum mechanics, which describes the world of the very small with flawless precision. And we have Einstein's general relativity, his theory of gravity, which describes the world of the very large planets, stars, galaxies. also with flawless precision.
But they don't work together.
They hate each other. They're written in different mathematical languages, and they give nonsensical answers, infinities, when you try to apply them in the same place, like at the center of a black hole.
So we don't know if gravity itself is a quantum force.
We don't. Is there a quantum particle of gravity? A graviton. Is space-time itself smooth and continuous, or is it made of tiny pixel-like chunks at the smallest possible scale? We have ideas like string theory or loop quantum gravity, but we don't know the answer yet.
Unifying those two theories is the holy grail.
It's the theory of everything that physicists have been dreaming about for a century.
And what about the tech? The big one we've only touched on is quantum computing.
Right. That's where all of these principles, superposition, entanglement, come together in the ultimate application.
So just to be clear for everyone listening, what is the fundamental difference between the computer on your desk and a quantum computer?
Your computer works with bits. A bit is a switch. It can be on or off. A 1 or a 0. It's binary. A quantum computer works with qubits. And thanks to superposition, the same principle as the cat being alive and dead, a qubit can be a 1 and a 0 at the same time.
So it's not one or the other, it's a blend of both.
Exactly. And if you have 2 qubits, you can represent 4 states at once. 3 qubits, 8 states. It scales exponentially. If you can build a quantum computer with just a few hundred stable qubits,
you get this astronomical computing power. The source says they could solve problems in seconds that would take our best current supercomputers millennia.
Literally thousands or even millions of years. It's not just a faster version of what we have, it's a completely different way of computing.
What kind of problem needs that kind of power?
The biggest one is simulating reality itself. If you want to invent a new drug, you need to simulate how a complex molecule will fold and interact with proteins in the body. That's a quantum problem.
And classical computers are bad at simulating quantum mechanics.
They're terrible at it. It takes an insane amount of memory. It's like trying to build a perfect flight simulator using only Lego. A quantum computer simulates quantum nature natively. It speaks the right language.
So we could discover new medicines, design new materials for perfect solar cells or batteries, maybe even create truly accurate climate models.
That's the promise. A revolution in science and engineering.
It really feels like we're just at the beginning. Like we've spent 100 years learning the alphabet of the universe, and now we're about to start writing sentences.
I think that's a perfect metaphor. We know enough now to understand how much we still have to learn, which is a much better place to be than in 1900 when they thought they knew everything.
It's way more exciting. Okay, let's bring it all home. We have thrown a ton of concepts at people today, so let's do a quick cheat sheet. If you're at a party and want to sound smart, what are the 5 key ways quantum mechanics is already running your life?
Right, let's do it. Number 1, lasers. Comes from quantum coherence. It's in your phone, your Blu-ray player, your internet connection, the doctor's office.
Got it. Number 2, secure communication. That's entanglement. The future of unhackable data for banking, government, everything.
Number 3, faster computing. Well, future computing. Using superposition to solve currently impossible problems in medicine, materials, and beyond.
Right. Number 4, better measurements. Using squeezed light and other quantum tricks to sense the world with incredible precision, from gravitational waves to maybe even tiny magnetic fields in the brain.
And number 5, medical breakthroughs. Using those spectroscopy techniques to see what's happening inside a single living cell to understand and fight disease at the most fundamental level.
That is a hell of a resume for a theory that started with people getting angry about a cat in a box.
It is. And I think the real takeaway is that this stuff isn't magic. It feels like it. But it's just the real rules of the universe. We're just finally learning how to read the user manual.
And like Dr. Scully said, the adventure is just beginning.
It makes you think. If the last century took us from that thought experiment to the smartphone and mapping black holes,
what on earth is the next 100 years going to look like?
Are we going to finally unify gravity? Are we going to understand dark matter?
Are we going to be able to manipulate reality in ways that we can't even imagine right now?
I've learned not to bet against the weirdness.
Me neither. The universe is pretty good at blowing our minds.
It certainly is.
Well, that's all the time we have for this one. Thanks for diving into the quantum realm with us.
It was a pleasure.
Keep asking questions, and we'll catch you on the next Deep Dive.